going to look at how we can find a posterior existence probability in tracking methods that use existence probability as a track quality measure. And one example of such a tracking method is the integrated probabilistic data association, also known as IPDA. So what we want to do, we want to find this thing I call it R, which is the probability of existence given all the measurements. That's what we want to find. And how we're going to do this is that we're going to use total probability expansion over all the association hypotheses that we can have. So this is working in the IPDA framework, so where we have m measurements and then m+1 possible association hypothesis, one for each measurement. So these are the A's we're talking about. So let's first look at the probability of existence. Given that such an A equals 1, or equals such that equals I, which is greater than 0, that probability is just 1. Because if you are able to associate the measurement to the target, if the target has given rise to measurement, then clearly that target must exist. What is a lot more complicated is the probability of existence conditional on the hypothesis that no measurement came from the target. So in this case, we're going to use bias rule to make this is long enough sense of this. So what we have here is a probability that A equals 0 given existence and a higher probability of existence that we have from the previous estimation cycle. Then we have a normalization constant, which is this plus the probability of A equals 0 conditional on non-existence. So I just say that out. This is how I write that. This symbol for negation of E, the sense of existence. And I think a bit about what are all these things. Well, if the target exists and I don't have any detection from it, then I have a misdetection. So this is the probability of misdetection, which is 1 minus the probability of detection. This thing, probability of existence, what is that? Well, that's what I get from the previous cycle. I just call that R. I write R predicted in the book, but I don't want to write all this case now, so just put it R. What about this thing? Probability that I don't get any measurement from the target, conditional on non-existence. Well, if the target doesn't exist, clearly I cannot get the detection. So this probability is 1. This one probability of non-existence is obviously 1 minus R, which is the existence probability. So let me try to summarize what this is a bit simpler. So now I have this one, this is this, and I have this one, this is this in the numerator. So this is simply 1 minus PD times R. In the denominator, things get a little bit more complicated because now I have this R here, and this is something I can cancel against this R, so that I'm left with this 1, and then minus this PD times R. So I get 1 minus PD times R. So you see this expression I get for the existence condition on misdetection, it has this kind of nice, slightly broken symmetry. Then the next step now is that I need to say something about the probabilities of the association events. And then I'm going to base this on what I already have done for the PDF. So I need to record that result. So I'm just going to use the Poisson assumption immediately, just looking at that case. Forget about the diffuse case I have. Then my expression I had, probability of the association with A, given all the data, they are proportional to either this lambda, also a density of vector times the misdetection probability, or it was the detection probability times this language object. So then we need to modify this to take into account that we had that we now can have existence or non-existence. So then I need to look at how did I arrive at this. Where did it happen something that existence could affect? So then I did some probabilities of the number of measurements. So remember I use this M bar for realization. So the probability that the total number of measurements has a particular value, given that the number of vector measurements for ones have the same value. That was 1 divided by 1 minus the detection probability. And then I also had similar probability. Now conditional on 5 number of vector points. N bar minus 1. So the reason why I bring this up now is because existence affects the number of measurements that you can expect to get. And this is quantified by these probabilities. So we need to think about then what happens when existence is important. Are these expressions going to be the same as they were, or are they going to be something different? Going to modify that, something slightly different. So now the probability that the number of measurements attain some particular value, given the number of false alarms attain the same value. What is really that? It's clearly that this is the case if there is no measurement from the target, so this is 1 minus the probability that the target exists. And that it also is detected. Now, if existence is uncertain, then this is going to be the same as the probability of this probability is going to be the same as the probability of detection. Conditional existence times the probability of existence. And since probability of detection is the same, it's just it's constant, then I end up with this expression. So now you see how 1 minus PD was transformed into 1 minus PD times the existence probability. And then we look at the other probability of n attaining some particular value, given that the number of resonance is that value minus 1. So this can only happen if I have a detection from the target, so this must be the probability that the target exists. And is detected. And this is the same as the probability of detection, conditional existence, times probability of existence, which is PD times R. So this is the only place where existence enter the picture. So then I can just make these substitutions, this instead of this and this instead of this, to get the IPDA event probabilities. Now again, we talk about the probability of A, but remember now that this is different from what I did here. I did it for the PDF, now I do it for the IPDA with the existence uncertainty. So then I really have all the things I'm going to stitch together. What I'm left with is now the total, to use the total probability theorem, and then I'm going to get a bit of algebra that I need to deal with. So, I'll use the total probability theorem. First, I spell it all out, but this is really I think evaluate. So, first, I have one contribution from this detection hypothesis, so probability of that, and probability of existing condition on that. And then I'm going to have contributions from all the measurements. Of course, all of these probabilities are 1, but the other ones are something I was did evaluate. Now, what I have. What I have here is only up to proportionality, so I need to include a normalization constant. since there's no such assumption here, it's the actual probability, so I need to include that. It's going to be the same normalization constant, both for these and for these. And that normalization constant will look like this. This, and then it's the sum of all these things. I guess the sum of all that becomes normalization constant. Then I have this thing from over here. It's going to be in circle instead of this one. Then now I'm going then to insert this thing. And then I'm going to insert this thing. Remember that this is 1. Okay, so I kind of have my expression here, but let me manipulate it a little bit more. Get something that looks a bit more similar to what they had in the book. Is there something I can simplify? Yes. This and this cancels. Then this is going to look a bit nicer. So let me just write it on a single fraction line. So now from here I have 1 minus PB times R times lambda. And this one. There I have what I have. Nothing happened with the denominator so far. So what can I do with this? Yeah, I'm going to take this lambdas. I'm going to put them over here by dividing by lambda in both up and down. The PD I can take out of take the PD out of the sums. There's a few things like that. This R here, I can put it outside of the whole thing. I'll just do that. So then I get the sum of only these likelihoods. Now, since I divide by lambda both up and down, I'm going to get minus PDR here, no lambda anymore. Detection probability times the existing probability here divided by lambda, again same sum. So this is starting to look similar to what I have in the book. So I'm just doing one more step. So I'm not going to do anything more with the numerator now. But the denominator is still a little bit not of the same form. So what I'm going to do here is that I'm going to add and subtract the existence probability. Let me just do that. So then minus R, and then when I do that, then So this R here, that's just for cancelling this R that came here. And then I have R and minus PD, which is this thing. Then of course I also have an R in this multiplied by this sum, which is this R. Now you can recognize what I call the calligraphic L so it's this whole thing that is written in this square bracket, which is the same as you have in the numerator. So this is the standard expression for the existence update in the integrated probabilistic data association. But of course, you see that the last part there was just a bunch of algebraic manipulations, and there are many other variations that you could use instead to express exactly the same mathematics.